Okay, so I guess before I get started, I will let me show you some of the content I've posted so you can practice for the final exam. So, this is planned for week 6 Monday, but week 6 Monday is a holiday, so we're having the lecture today and right now, and so anyway, we'll deliver today's lecture right now, and then I will and I've also posted all of these practice problems. So this first thing is actually just a formula sheet. It's not required or anything like that, but the final exam is open book, and I thought it would be helpful or handy for you to have kind of a place where you can have all of your all of the formulas in one location. One exception is that we never covered confidence intervals for proportions two samples, and so this I'm sorry. We never covered confidence intervals for proportions two samples. So this one section you can kind of ignore, okay? But everything else I believe is helpful and handy. Kind of just going back to that formula sheet. You can see in here it gives you the formula for the interval itself, the formula for any kind of test statistic and standard error. So also for hypothesis test, it lists off what the hypothesis would look like, as well as any what the standard error is, what your test statistic is, what how these things would go about. Okay. The final exam is going to focus much more heavily on content from chapters 7, 8, and 9, or really, I would say mostly chapters 8 and 9. Okay. And so it's the final exam is not cumulative in the traditional sense. So there might be so let me talk about this a little bit, but I've posted a practice final, and you will see in the practice final there are different questions, but most of it's going to be coming from chapters 8 and 9. There might be a couple definition questions or conceptual questions that don't involve any kind of calculations that come from some of the earlier chapters, but the bulk of the final exam is going to be statistical inference. So that will be how that goes. So I posted some problems, chapter 8 practice problems, okay, and then some chapter 9 practice problems. Okay, well, it says error. Giving me that, but it should be there. Okay, chapter 8 practice, chapter 9 practice, also some conceptual practice problems. I realized these conceptual practice problems that I've posted perhaps overemphasize type 1 and type 2 error, and maybe the conceptual problems that I put on the final exam will focus on content other than just what is type 1 error and what is type 2 error and what do they mean, but they're there, okay? And then the answers to all of these practice problems that I've posted, as well as answers to the practice final, are available. So I think so my hope is that this will be I guess adequate practice, or provide you yeah, a decent amount of practice to kind of to prepare so you feel ready for the final exam. So, after today, I won't see you again until Wednesday, and Wednesday will be the day of the final. So, okay. Any questions about the final before I kind of jump into today's content here? Okay, so here's today's lecture, and forgive me for leaving it up as week 6 Monday, but yeah, this is what we're looking at. Okay, so I'm going to kind of just blitz over this textbook problem very quickly. So this one is asking you to do some statistical inference, and here in this problem, we give you the numbers of the sample directly. All right, so it says the weights of 4. I wrote tomatoes, but probably potatoes is actually going to be a better situation here, because I don't think they sell bags of tomatoes so much at the grocery store, but they do sell bags of potatoes. So anyway, let's say you buy a bag of potatoes. It's labeled 5 pounds. And you decide you're going to weigh how much these bags actually weigh. They say 5 pounds on the label, but are they actually 5 pounds? Maybe not. We measure them, and these are the weights: 5.1, 5.0, 5.3, and 5.1. And then it says make a 95% confidence interval, and based on that confidence interval, is there enough evidence to reject and say the average weight of bags is something other than 5 pounds? Okay, so to approach a problem like this, where you're given the values directly, you have to kind of figure out your summary values yourself. So you'd have to calculate the mean, and you'd have to calculate the standard deviation. Those are, I guess, concepts from earlier. So, I think it's probably a good idea to just have on your formula sheet, how you find the standard deviation or something. Finding the mean, I imagine you already have memorized. No need to write down the formula for that. But the mean is, you add up your numbers and you divide by 4, and then the standard deviation. Once you find the mean, you subtract you get the difference from each value from the mean. You square that difference, divide by n minus 1. After adding them all up, and then you take the square root. Okay, here I showed using R and whatnot, and then we'll get the critical value T from the T table, and then once you have that, you can plug everything in to get your confidence interval. So I have X bar plus or minus T star times S divided by the square root of n. So 5.125 plus or minus our critical value T, 3.182, coming from the T table, divided by the standard deviation S, which we found using the formula, divided by the square root of n, divided by root 4. And our resulting confidence interval goes from 4.9 to 5.3. And the question is, does this provide evidence that there is a difference, or that it's different from 5? Okay, do we have, does the data provide evidence that the mean weight of, potato bags is something other than 5? Because the mean of our sample is 5.125, and is that significantly different from 5? So, our interval contains the number 5. It goes from 4.9 to 5.3. So 5 is in between there. So we have to say we don't have evidence, or we don't have enough evidence to say that it is different from 5 pounds. Okay, so the interval does capture 5. 5 is in between these two, the endpoints of the numbers. Okay, 4.9 is lower than 5, and 5.3 is higher than 5. So 5.0 is in between the endpoints, and that means 5.0 is a possible weight, and we can't reject or say that we have evidence that it's definitely different than 5. Okay. I'm going to skip over this part here. We're going, you do a hypothesis test, and you set up your hypotheses, and well, I guess maybe I'll talk a little bit about this. If we make a 95% confidence interval, and this is the result going from 4.9 to 5.3, we would say we do not reject, or we don't have evidence that there's a difference. Okay, and so doing a hypothesis test using the same data, we should come to the same conclusion. The same conclusion being that we cannot say that the mean of the population is different from 5 pounds. So, so if we were to run a hypothesis test, we would not reject the null hypothesis, okay? Because our confidence interval says we don't have evidence that the mean is different from 5. The hypothesis test will give the same conclusion, right? So the key idea here is that a two-sided hypothesis test, if you're using alpha of 5%, will give the same result as a 95% confidence interval, as far as the conclusion goes. Where a 90% confidence interval will give you the same result as running alpha equal to 10%. A 99% confidence interval will give you the same kind of conclusion as doing a hypothesis test with alpha 1%. So, whatever two numbers add up to 100%, those are, you're going to get the same answers when you do a hypothesis test or confidence interval. Oops. So the confidence interval did not provide evidence that there's a difference from 5, and therefore the corresponding hypothesis test will also come to the same conclusion. We don't have evidence that it's different from 5 if we're using alpha equal to 5%. Okay, so if we wanted to actually set up the hypotheses, these are just some key reminders. Always use the mean mu, all right? Never X bar. Always have an equal sign in the null hypothesis. And here we have a two-sided test, okay? Confidence intervals, when I say confidence intervals and hypothesis tests will give the same result, it only applies when you're doing a two-sided hypothesis test. So I have mu equal to 5 versus mu not equal to 5. And we'll go through, we'll check all of this. And then as far as the calculations go, the statistics that we have X bar is 5.125 and the standard deviation is 0.1258. And again, we found these kind of ourselves when we did the confidence interval. We took the actual values and we did this. And again, the point with the hypothesis test is we're saying, if the null hypothesis were true, if the mean truly was 5, then we would expect our random samples to have a mean of around 5 as well. And we have a mean of 5.125, and is that significantly different? And the answer is, well, we go through our calculations and we go through to get our p-value. And it turns out that the difference between 5 and 5.125 is not statistically significant, right? We go and calculate our test statistic. We say we got 5.125. Our expected value is 5. We're going to divide by our standard error. This is around 1.987. This is kind of like our z-score, except it's for the t distribution. And in the case of the t distribution, we need the degrees of freedom. We have n-1, 3 degrees of freedom, right? So this is kind of the biggest difference when dealing with the t distribution over the z distribution, is that you now have to account for your sample size. Sorry, I'm gonna just move. So I'm a little, I'm not directly in the sun over here. Better for me. Okay. So we have 3 degrees of freedom. And when we look this up, we're looking at this row for 3 degrees of freedom. And we ask, where does this number 1.987 fit? Where does 1.987 fit? 1.987 fits in between these two numbers, 1.638 and 2.353. And so as far as calculating our tail areas, we look at the column headings and we'd say, you know, if our T value was exactly 2.353, which doesn't happen all the time, but you know, it's not impossible. If you got 2.353, then your tail area would be exactly 0.05, okay? And if you had exactly 1.638, then your tail area would be exactly 0.1, right? And we're getting a number that's farther away from 0 than 1.638. So that means the amount left over in the tail has to be less than 10%, but it's not as far as going as 2.353. So whatever is in our tail has to be more than 5%. So our tail area is going to be something between 10% and 5%. And because our alternative hypothesis is two-sided, we're going to double that. And our resulting p-value is going to be between, you know, double 10%, double 5%, somewhere between 20% and 10%. And that's going to be the answer there. And if our p-value is between 10 and 20%, and our significance level is 5%, our p-value is bigger than 5%. And so, so because we know our p-value is bigger than 5%, our p-value is bigger than 5%, we're not going to reject the null hypothesis. And we're going to say we don't have evidence that the mean is different from 5 pounds. Okay. All right. So, you know, if you watch Wednesday's lecture, this is a lot of this is kind of review from Wednesday's lecture. And so let me introduce kind of the new topic for today. The new topic is that now we want to be able to compare the means of 2 populations. Okay, so and there's actually 2 scenarios that we might have to deal with. One is we could be dealing with independent samples, and we have 2 separate populations. Okay, and then the other is we could have 2 samples, but the samples are paired. And this is actually just one population. It's just one population, but you got 2 measurements from the same population. So that's also a possibility here. Okay. So we'll go over a couple examples and we'll kind of talk about this. So here's an example. And I want you to ask, are these 2 separate populations? Or is this really just kind of like one set of measurements? Is, you know, every value is paired with another measurement as far as the paired samples go. So in paired samples, every value has a partner or is paired with another value. Okay. Whereas independent samples, that's not going to be the case. You know, one indication that it's definitely not paired is that if your 2 samples have different sample sizes. Okay, if you have 2 samples and they're different sample sizes, then they can't be paired because in paired data, every value has to have a partner. And if you have 2 different sample sizes, then they certainly cannot be paired. If you have 2 samples and they're exactly the same size, they might be paired, they might not be paired. It's not necessarily the case, but if they're not the same size, then we know for sure that they are not paired data. So here it says, we randomly selected from some adults from the United States, and we asked them to kind of rate their thoughts on a new potential soft drink. And then we also asked some randomly selected adults from the United Kingdom and asked them to rate their soft drinks. And we wanted to see, like, is there a difference in kind of the ratings from the Americans versus the ratings from the British, right? Is there a difference between the ratings that they've given these soft drinks? And in this case, the numbers from these two samples, they are not related to each other. All right. What the Americans say and what the British say, they're both kind of looking at the same soft drink, but as far as the data values go, they're not connected. These two samples are independent. All right. So we're going to treat these as independent samples. Okay. Here's an example where they would be dependent or paired. Okay. Here we have a random selection of adults, and we give each adult 2 drinks, right? We give them a drink A and a drink B, and we ask them, rate drink A, rate drink B. And we want to say, do people prefer drink A, or do people prefer drink B, or, whatever. So in this case, as far as the population goes, there's really just one population and you're getting 2 measurements, right? So each adult, the same adult provides the score for drink A and drink B. And so these 2 scores are related to each other because they're being generated by the same person. And so we can take every drink A score and pair it with a drink B score, right? So these scores are paired and treated as dependent, okay? Versus the one in the first example where we have some Americans and people from the UK, we can't necessarily find a way to pair them, okay? Unless we go through some, I would say, in some studies, you can pair seemingly unrelated, but you have to kind of pair them based on, say, certain characteristics or demographics. So you might try to do some kind of study and you'll say, okay, we got some people over here and we'll try to pair their data with people over here. And we're going to say, okay, this person was male, age, 30. We're going to try to pair them with a person in this data set who is also male and age 30. This person was female, age 25. Let's try to find them a match with another female, age 25. And you might try to kind of pair your data in that way and see, is there a difference between, opinions in city A versus city B or something like that. So that's a possibility. But if it doesn't mention any kind of effort like that to pair the data, then it's going to be an independent situation. Okay. So when we're dealing with independent samples, the question is that we're asking is, do their respective populations have different means? So you have sample 1 and sample 2. Sample 1 comes from population 1, and sample 2 comes from population 2. And the question is, do their respective populations have different means? Okay, and so the picture is something like this, where you have a big population, population 1. You have a big population, population 2. Population 1 has mean mu1. Population 2 has mean mu2. But we're not able to observe these populations directly because they're populations. And the whole thing with the population and the whole point of statistics is that, we can't observe the populations directly because they're too big. And so instead, we will be, we take a sample from population 1, we take a sample from population 2, and we're able to see all the values in sample 1 and all the values in sample 2, okay? And from sample 1, we can get the mean X bar 1, and from sample 2, we can get the mean X bar 2. Also the standard deviations in the sample size, S1, N1, S2, and N2. But this is only the values we get to see. We only get to see the values in the samples but not the populations. And the question is, based on the X bar 1 I see here and the X bar 2 I see here, can we say that the respective population 1 and population 2, do they have different means? Or is it possible that the two populations actually have the same mean? Okay, so one thing we can do is we can create a confidence interval, and we're going to create a confidence interval for the difference between mu1 and mu2. Okay, and basically, if we can say, there's no difference, if that difference between mu1 and mu2, if that difference could be 0, then the two populations could have the same mean. That's what we want. Or on the other hand, if we're pretty sure that mu1 minus mu2 is not 0, then we can say, okay, then the population is definitely, the two populations definitely have different means. Okay, so this quantity mu1 minus mu2 is, how much does population 1 differ from population 2? And we want to know, could that difference be 0, or do we have evidence that the difference is not 0? And if it could be 0, then the two populations could have the same mean, versus we can say that they're definitely not 0. So again, we're not able to get this exact value of mu1 minus mu2 because we can't see the populations directly. So we're going to create a confidence interval, and we're going to use the difference between our two samples. We're going to do X bar 1 minus X bar 2. That's going to represent kind of our starting difference. And then we want to see, okay, is there a difference there? Okay. So, just an example of what the resulting confidence interval could look like. If you said, let's create a confidence interval for the difference between the average height of adult men and the average height of adult women. Okay, so again, there's if we assume, we looked at samples of adult men, samples of adult women, we measured their heights, and we say, okay, create a confidence interval for the difference in the average heights. Okay, that confidence interval could go anywhere from, say, 4 to 8 inches, 4 inches to 8 inches. Okay, maybe around 10 to 20 centimeters. And we would say something like, I'm 95% confident that the average height of adult men is somewhere between 4 inches and 8 inches taller than the average height of adult women. We're not saying anything about what is the height of average, what is the average height of men alone, and we're not saying anything about the average height of women alone. We're just talking about the difference, and we're saying, if there were to be, quote unquote, an average man and a quote unquote average woman, if such a thing were to exist, what is the height difference between average man and average woman? Well, we're saying I'm 95% confident that there would be a height difference, and that height difference is going to be somewhere between 4 inches and 8 inches, that the height of the average man is going to be, higher than the average height of the average woman, and they'll be somewhere between 4 inches taller and 8 inches taller. Okay. And basically we're saying, yeah, I'm pretty sure it's not going to be 0. Okay, that the difference between these heights is not going to be 0. And so we can say we have evidence that the height of the average man is higher than the height of the average woman. Okay. And so we'd say we have evidence that there is a difference. So this is the formula for making a confidence interval, all right? And so just jot this down in your notes. It's also in the formula sheet. You can put a star on this page. Basically, you need to have all of these values. It's just an ugly formula for the standard error, but you just kind of have to gather all of these values from your data. And it's just a matter of plugging in these numbers. Okay, this part is the standard error. And then when you multiply the standard error by your critical value t, that's going to be your margin of error. So let's go ahead and try out an example and plug the values in. Oh, one thing is when you look up your critical value t from the t table, you need a degrees of freedom. And the degrees of freedom, when you're dealing with two independent samples, it's actually kind of complicated. And it's a complicated formula. I don't want to get into it. So we're going to just kind of ballpark it and use a shortcut. The shortcut is, we just approximate it. We're just going to use n-1, okay? However, we have two different n's. We have an n1 and an n2, right? You have two samples. And so you just take the smaller sample size. So if you have 10 observations in one sample and 20 observations in the other sample, your n1, you have two n's, 10 and 20. You take the smaller one, 10 minus 1, and we're just going to work with 9 degrees of freedom. Okay, and that's an approximate thing. It's that's playing it safe. That shortcut will underestimate the degrees of freedom than what the true degrees of freedom are, but it's good enough in most circumstances. Now, other textbooks that you read might give you a shortcut that overestimates the degrees of freedom, and you can and they might say, do n1 plus n2 minus 2 or something, and that will tend to overestimate the degrees of freedom that you have. It's generally safer to underestimate your degrees of freedom than to overestimate. Okay, it's safer that way. So this formula underestimates the degrees of freedom. We're just going to use n-1 using the smaller of n1 and n2. All right, so here's a simple, silly example. We're going to say, I had this idea from like, my kids have these toys where, you have these different shaped blocks, right? The circles and the squares and the triangles, and you have to get them to fit into, this box where there's like where they have cutouts, the triangle shaped cutout and the square shaped cutout and the circle shaped cutout and this and that. And anyway, I was just curious, I wonder if there is a dexterity difference between young adults and seniors, and I don't know if this is legal to do in a job setting, but let's say, we conducted this test and we had 20 young adults participate, and we said, okay, how many can you complete within the given amount of time? We had 15 seniors. We'll say seniors are age 62 or older or something. And we asked, how many can you complete in this given amount of time? And we'll say the young adults were able to complete 28.2 with a standard deviation of 4.3. So again, some were faster, some were slower. And then the seniors were able to complete 24.3 with a standard deviation of 5.7. So we got 28.2 versus 24.3. So a difference of almost 4, a difference of 3.9, right? You do, what's the difference between these two numbers? So it looks like the young adults were able to complete more, 3.9 more than the seniors. And the question now is that difference of 3.9, is that significantly different from 0? Or is it possible that there's actually no difference, that the difference is 0, but we just happen to get a difference of 3.9 by random sampling? So we're going to start by creating a confidence interval, right? We'll just plug in our numbers. We'll call young adults group 1. So my N1 is 20. My X bar 1 is 28.2. My standard deviation S1 is 4.3. We'll call the seniors group 2. So N2 is 15. X bar 2 is 24.3. S2, the standard deviation is 5.7. And so we just kind of take all of these things. I've labeled them all here. So I would say that's an important step when you're doing your problems, is to just label your numbers. I would say avoid the temptation of just going through the problem and directly just starting to fill in your formula here. It's very easy to make a small mistake somewhere along the way. So just take a moment and label all of your values. And once you have them all labeled, then plug them in. So if I plug in these numbers, 28.2 minus 24.3, I get 3.9 plus or minus my critical value times the standard error. As far as the critical value goes, we're gonna say how many degrees of freedom do we have? I have two n's, I have 20 and 15. I'm gonna use the smaller one. So I'm gonna do 15 minus 1, 14 degrees of freedom. And if I go, let me pull up my reference tables. Okay, so going to 14 degrees of freedom, 95% confidence, the number I have is 2.145. Okay, 95% confidence, 14 degrees of freedom. I'm going to use 2.145. So if I plug all of this in, I get, after multiplying this out, I get 3.9 plus or minus 3.77. So my interval goes from 0.13, positive 0.13 to positive 7.67. Okay, and I'd say I'm 95% confident that the number of blocks completed by the senior, or that the difference between the average number of blocks completed by the young adults and the seniors is somewhere between 0.13 and 7.67. Okay, so could it be 0? Could our interval, when we make a 95% confidence interval, it doesn't contain 0, right? Our interval is entirely positive. It just misses 0 by a little bit, 0.13, but it's still above 0. So kind of on the low end, we expect young adults to complete at least, 0.13 of a part more than the seniors. And then maybe on the high end, they might be completing as much as, 7.5 parts more than the seniors, but, maybe something in between in there, right? But whatever it is, we're pretty confident that the young adults can do more, right? Because 0 is not within the bounds of the interval. So we'd say, you know what, I'm pretty confident that the difference is not 0, that there actually is a difference, okay, between the average number of blocks that are completed. Okay. When we did this, I arbitrarily said young adults we're going to call group 1 and seniors we're going to call group 2. What if I had switched these labels and I said seniors are group 1 and young adults are group 2? Okay, so then all of these values would become, X bar 2, S2, and N2, and all of these would be X bar 2, S2, and N2. Or I'm sorry, X bar 1, S1, and N1, and these ones would all become the 2s. So we would kind of switch the groups, right? Young adults versus seniors, or seniors versus young adults. When you make the confidence interval, however, the only thing that really changes, okay, is that now instead of 20.2 minus 24.3, we get 24.3 minus 28.2, and we get negative 3.19. Your critical value T remains the same. And then if you look at the formula for the standard error, sure, you're switching all of these things, but you're adding them together. So the order in which you add them together doesn't matter. You're going to get the same standard error. You're going to get the same standard error as you did on the previous slide, 1.758. And when you multiply them together, you still get 3.77. So now I get negative 3.9 plus or minus 3.77, and I get the interval ends up being exactly the same, just negative. All right, so here I get negative 7.67, negative 0.13. Over here I had 0.13, positive 0.767. So kind of flipping between these two slides, we get the same thing. It's just one is negative of the other. And so this one we're saying, I'm 95% confident that the average that the seniors can complete is between 0.13 and 7.67 fewer, because it's negative, than the young adults. So the other one said, I'm confident that the young adults can do more than the seniors. And here I'm saying I'm confident that the seniors can do fewer than the young adults. We're basically saying the same thing. It's just, what's our point of reference, right? Are we saying the young adults can do more, or we're saying the seniors can do less? We're both basically saying the same thing, okay? And in this case, again, 0 is not within the bounds of the interval. So we would say we have evidence that there is a difference. Okay, I went through this fairly quickly because we've seen confidence intervals before, and I think it's pretty safe. Or I think you're fairly familiar with it. So maybe at this point, maybe you still need some more practice. And so I've released some practice problems for you, but we've seen confidence intervals before. Okay, hypothesis tests, same thing. Let's use the same data. We go through, we set up our hypotheses, we check conditions, we calculate a p-value, and we make our conclusion. So using the same data, we'll set up our hypotheses. Our question says, is there evidence that there's a difference in the average number of blocks completed by young adults and seniors? So here I'm asking, is there a difference? Meaning we're going to have a two-sided test. We're not suggesting at this point that one group is able to complete more than the other group. So we're just asking, is there a difference? Okay, so here, when we write our hypotheses, these are the same rules that I kind of write on all of our hypothesis slides. In this case, we have two populations. So we're going to have two mu's. We're going to have a mu1 and a mu2. Our null hypothesis is that the two means are equal to each other, that mu1 is equal to mu2. That's your null hypothesis. The alternative will be that they're different, that mu1 is not equal to mu2, that there is a difference between these two population means. Mu1 is different from mu2. Okay, we'll check our conditions. All of these conditions are met. So we'll go ahead and calculate our p-value. So using the same formulas for the standard error, and we're going to ask, how significant is the difference that we observed? We observed a difference of 3.9. Okay, one group has a mean of 28.2 and the other has a mean of 24.3. That's a difference of 3.9. Is that significantly different from 0? Okay, or could that difference be the result of random chance? Okay, well, the confidence interval said it is significantly different from 0, so our hypothesis test should make the same conclusion. We should end up getting a p-value less than 0.05, but let's go ahead and do our work here. We calculate the standard error. This is the same formula that we used for the confidence interval, same standard error formula. Standard error is 1.758. Okay. Our test statistic here is, okay, well, how much did what did we observe in our data? We observed a difference of 3.9, right? X bar 1 minus X bar 2, 28.2 minus 24.3. We got a difference of 3.9. If the null hypothesis were true, what difference would we expect? If the null hypothesis were true, mu1 is equal to mu2, we would expect our random samples to have a difference of 0. Of course, because of random chance, and we don't expect it to be exactly 0, but we would expect the differences to be around 0. And we got a difference of 3.9. So the question is it significantly different? So we compare that to our standard error. So in the numerator, I have 3.9, and then I'm going to divide by my standard error of 1.758. And so I get a t of 2.218, t of 2.218. So I observed a difference of 3.9. If the null hypothesis were true, I would expect a difference of 0. It's kind of silly doing minus 0. So a lot of formulas, we just throw away the minus 0. We're just going to have X bar 1 minus X bar 2. And we divide by the standard error. And we're going to look that number up, 2.218, in our t-table for 14 degrees of freedom. So looking at 14 degrees of freedom, 2.218 is in between these two numbers. It's in between 0.025 and 0.010. Okay. So we're between 2.145 and 2.624. Our tail area is between 2.5% and 1%. And so we have a two-sided alternative. Our hypothesis is two-sided. So we're going to double that. And our p-value, we don't know exactly what it is, but we know it has to be less than 5% and more than 2%, right? If I double 2.5% and double 1%, it's going to be between 5% and 2%. We don't know exactly what it is. If my test statistic was exactly 2.145, it would be exactly 5%. And if it was 2.624, it would be exactly 2%. But we're getting 2.218. So whatever it is, it has to be less than 5%. has to be more than 2%. And if that's our conclusion, or if that's the result, our conclusion is going to be we reject the null hypothesis. Okay, our significance level is less than 5%. So we'll go ahead and reject the null hypothesis, and we'd say we do have evidence that there is a difference between the population means. So if the two populations do have the same mean, we expect our samples to have similar means. Is it possible that seniors and young adults can complete the same amount and just by random chance, we got a difference of 3.9? It's possible, but how often does that happen? Okay, it only happens around, it happens less than 5% of the time, okay? And because that probability is low, our results are considered to be unusual. And we would say, you know what? It's low enough that I don't think it happened by random chance. It's low enough that I don't think it happened by random chance. And so the fact that we did get this result that is quote unquote unusual tells me that, you know what? The reason why I'm getting this difference of 3.9 isn't that I just got this lucky random fluke, but rather there actually is a difference in the abilities of young adults and seniors. And that's why I'm observing this difference of 3.9. There's actually a difference in abilities. Okay, that's hypothesis testing and confidence intervals for two independent samples. It's a lot of stuff, and we went through it fairly quickly. The reason for it is we've seen a lot of this before when we were dealing with proportions, comparing two proportions and doing hypothesis tests there. And a lot of the principles are exactly the same. A lot of the conclusions and ideas are exactly the same. The only kind of key difference is your formula for the standard error is different, and the way you use the t-table is different. But the logic and the conclusions and how you use your significance level, that's all the same. Here, I'll wait for this airplane to fly by. Okay, our last topic, and then I think we can just kind of end a little bit early. We will compare means of paired samples. Okay, so you have paired data if the same person is kind of providing two measurements. So a very common scenario for that is before and after. If you take a measurement before something and then you do something and then you measure their values after, that would be a before-after situation. Okay, you can also have twin studies, and you can kind of compare, one twin versus the other twin. And then you have matched pairs. Okay, matched pairs is, you have two different groups, but you're matching each individual in one group with a corresponding individual in the other group. You have each person kind of has a counterpart. And the key idea here is that you will compare one value with the other. Once you match these up, really, you'll just calculate a difference column. You'll just calculate a difference. You don't treat them as two separate samples or two separate populations. You just treat it as one population, and you just calculate a difference. And once you do that, it basically becomes either a confidence interval for one sample or a hypothesis test for one sample. You don't treat them as two separate values or two separate samples. Just treat it as one sample, okay? We don't care about the individual measurements. We turn everything on a difference to a difference, and then we just perform an analysis on the difference. So for example, so this is a silly question, but because this is not something you really ever think about, but if you're standing vertically and you smell something, is that different from when you're lying down and can you smell, right? Like if someone's cooking something in the kitchen and you're standing and you can smell it, That's one thing. And if you're lying down on the couch, can you still smell what's happening in the kitchen? And so we kind of asked, like, they had some kind of test to measure someone's smelling abilities, and I don't know what these numbers even represent, but these are the measurements that we got when somebody was sitting versus, or I guess sitting upright versus lying down, and their ability to smell. And we recorded these values, and the question is there a difference? Like, does your posture change your smelling ability? So even though we have two columns here, we're not going to treat them as two separate samples. Basically, this is just one sample, and we just have to calculate a new column called the difference. I just do one column versus minus the other. I calculate a difference, and now I just have one sample, and we're going to treat it as just one sample. Okay, so if I do sitting minus lying down, I get 0.25, I get 0.5, 1.25, and 0. These are now my values. With these values, just like kind of the very, very first example that we saw today, where you have just individual values, you have to calculate the mean, you have to calculate the standard deviation. So you'll just have to take my word for it. The mean of these four values is 0.5, and the standard deviation of these four values is 0.54, okay? So we calculate your mean and you calculate your standard deviation. And now that you have this one column of differences, and you have a mean and you have a standard deviation, then just ignore the other two columns. Just treat this as if you had just one sample, okay? And that's again, this applies only when you have paired data, right? There's, in the normal school year, these are on different days. And so there's a little bit of a break and you have some practice in between. You know, unfortunately, we're covering everything in one day. So I want to make sure you remember this applies only to paired data versus all the other stuff we saw way back here. This is for comparing two independent samples versus paired data, okay? So once you have this one sample, four values, okay, one mean, one standard deviation, now you can do a confidence interval, now you can do a hypothesis test. You're going to basically treat it as if you're doing a confidence interval for one sample, x bar plus or minus t star times s divided by the square root of n. This is the same formula you did when we did confidence intervals for one sample. And this is the results. And I'm just kind of skipping over this. I will let you check your, review these notes on your own time, okay? So if this is your resulting confidence interval, what kind of questions can you answer? And this is what you have. Sorry, I'm going over this. It's just kind of skipping over this because it's the exact same situation as having doing a confidence interval for one sample. Okay. And then a hypothesis test. Again, you're just basically doing a hypothesis test for one sample. It's just that we're asking, is the mean difference 0 versus not, okay? So now that you've calculated that difference column, we're asking, is that mean difference 0 or not? Or, you know, greater than 0 or less than 0, whatever situation you have. Sorry, the gardener is going to start blowing leaves here, and it's going to be loud. So I'll wrap this up shortly. If you're able to do a hypothesis test for one sample, this will be it, okay? So check your conditions. We'll ask, we'll compute the p-value, right? If the null hypothesis were true, we would expect our difference column to be 0, okay? Right, so we're asking, is the mean difference 0? And if that were true, then we would expect our difference column to just be 0. We have to, we'll have to kind of check here. And so we ask, you know, what's the probability that a random sample of 4 people end up with a mean difference of 0.5? And is that significantly different from 0? Okay, so you calculate your test statistics, X bar minus mu divided by the standard error. Same formula for doing a hypothesis test with one sample, and we get a t-score of 1.852 and 3 degrees of freedom. So and then we look this up in the t-table, 3 degrees of freedom, 1.852. We get a difference. Our tail area is going to be between 0.1 and 0.05. If we double that, our tail area is going to be between 0.2 and 0.1, and we would not reject the null hypothesis. Okay, and that would be our conclusion. Okay, so I know I went through that fairly quickly, but I'm hoping at this point it feels familiar enough that that we can work through it and feel confident in here. Okay, well, this is kind of all of the new material that I want to cover. I don't know if you had any questions about the final exam or preparing for the final exam. And again, I posted quite a few practice problems. So I will have office hours on Tuesday. And if you have any questions about any of the questions, the material, any of these practice problems or anything like that, I'll be happy to answer your questions on Tuesday. If not, have a great weekend. Good luck as you study, and we will see you on the final exam, or for the final exam on Wednesday. All right. Thank you, and have a good rest of your day.